All right, guys and gals, we're back with solving systems of equations yet again. This is elimination part 2. So at the first lesson with elimination, we just looked at the basics. How do we use elimination to solve a system? And I hope you realize that as you were solving, you only got one solution every time. And that was done on purpose. Today we're going to talk about a few things. One of the items we're going to look at is how do we know what type of solution we're going to have with elimination? Because, well, here's the problem. How do we know the type of solution we're going to have without having to go through the trouble of without having to go through the trouble of solving the system? Notice with graphing, it was easy. If we have one solution, well, there's an obvious intersection point. If there's no solution, well, then again, it was obvious we have parallel lines. If there were infinitely many solutions, then it would appear as if there were only one line on the page, when in reality, there are two, one overlapping the other. So again, how does this work when we're solving with elimination when we have no graph to go by? The answer is simple. All we got to do is look at that algebraic system and we'll solve, notice the quotations there, solve the system by what we call inspection. In other words, we're going to look at the situation and see what does it look like, right? And we can tell just based on what it looks like the type of system we're going to have. So remember, we've got three different options. We can either have one solution, so in other words, if we were to graph it, it would cross in one spot. We would have no solution. So again, we'd end up with parallel lines. Or infinitely many solutions. In other words, it would appear that we only have one line on the page when in reality there are two. So let's talk about the aspects of each one. So that way as we see these, we know what kind we've got. All right, the one solution scenario. Now, before we get too far into this, I do want to point something out to you. There are times when we're writing equations and we'll look at the coefficients. Remember, those are the numbers in front of the variable, and the constant. Here's something we got to do. If you ever see an equation like this one, the top one's fine, but if you ever see an equation like this at the bottom, notice we've got a coefficient of 4 and 2. We also have a constant of 4. If you can find a greatest common factor that's something other than 1, then you need to try to reduce the equation. For example, in this case, 4, 2, and 4 all have 2 as a common factor. Notice in this top case, though, I have a coefficient here technically of 1, 2, and 3. Well, 1, 2, and 3, the only factor those coefficients and constants have in common is 1. But if we look down here, 4, 2, and 4, well, they have a common factor of 2. So what I'm going to do is I'm going to simplify this equation. In other words, I'm going to divide everything in it by 2. So let's rewrite the system. So the system is going to look like this now. X plus 2y equals 3. All right. And let's look at this bottom one. If I divide by 2, I'd get 2x. If I divide by 2, I'd get negative y. If I divide by 2, I get 2. Now we can start comparing. All right. I know that we'll have one solution if both the left and the right-hand sides are different. And notice, these sides are different. These sides are different. But again, we're going to have to reduce our situation in order to be able to tell that. So anytime that happens, that's what we're going to need to do. Right? So again, I could say that this will have one solution for the simple fact the left sides and right sides of the equations are different. That means if I were to rewrite them in slope-intercept form, we'd have different slopes, different intercepts, we'd be good to go. All right, let's take a look at this next one. Well, different slopes for certain. Intercepts, maybe, maybe not, depends on the situation. Let's try the no solution scenario. Notice 1, 2, and 3, 1, 2, and 2. So both equations are set up with just greatest common factor of 1, so we're good there. Here's a no solution scenario. Look carefully. Notice how the x and y side are the same. This equals x plus 2. This one equals x plus 2. But x plus 2 here is going to equal 3. X plus 2 here, for some inexplicable reason, equals negative 2. So here's what happens here. This is a no solution scenario. With the x and the y, we'd end up with slopes that are the same, but our intercepts would end up different, just like they are here. Notice slopes are the same, but intercepts are different. If my left side is the same, but my right sides end up being different, sorry, we're going to have a problem here. This would be no solution. For the simple fact, we end up with parallel lines. Right? Now, infinitely many solutions can be kind of tricky to catch. For example, this first incident, not very tricky at all. It's the exact same equation. If we rewrote this to slope-intercept form, it would be the same line in both cases. So notice they are exactly the same. Okay, if you end up with something like that, well, then it's painfully obvious you'll have infinitely many solutions. All right. However, take a look at this next one. This one's kind of tricky. The second one kind of looks like our one solution. Notice the left and the right sides appear different. Okay, but I want you to notice something. 1, 2, 3, so greatest common factor of 1. Cool, that one seems to meet that requirement. But look down here. 2, 4, 6. They have a different factor, right, other than 1. 2 can divide into each of those. So let's rewrite the system. The top stays the same, x plus 2y equals 3. But I can divide each of these numbers by 2. 2 divided by 2 is x. 4 divided by 2 is 2. 6 divided by 2 is 3. Notice these end up being exactly the same. So again, we've got to be careful. If we end up with those that are identical, all right, then cool, infinitely many solutions. If we end up with some that look like this, where we've got one side the same but the others are different, then it's no solution. If we end up where they are totally different from one another, then we only end up with one. So that's one way for us to quote unquote solve the system. We have some idea of what we're dealing with before we ever get started. So let's look at some examples. Here we're not actually going to solve the system, we're just going to solve by inspection. And then we'll just very briefly explain how we arrived at our answers. So let's take a look at this first one. I've got -2, 6, and 1, so that seems to have a greatest common factor of just 1. I've got 5, -1, and 12. Okay, again, another greatest common factor of just 1. I notice that the left sides and the right sides are totally different from each other. So this should have one solution. And my reasoning is simple, that if I were to rewrite these, we'd have different slopes, different y-intercepts in this case as well. Yep, definitely just one solution. So again, left sides are different from each other, right sides are different from each other. Just one, and that would be my explanation. All right. Let's take a look at number 2. All right, well, at first, we seem to have sort of an odd situation here. The right sides are completely the same. All right, but if we notice here, the left sides are totally different. That's weird. But I noticed something. 4 and 2, as well as 0, all could be divided by 2 just fine. If I look here, 8, 4, and 0, all of those could be divided by 4. So I'm going to rewrite the system since I can simplify. This top, I'm going to go ahead and divide everything by 2. That way I can simplify. So we'll end up with 2x. I end up with a -y. And then, of course, 0 divided by 2 is still 0. All right, cool. Let's try this next one. We said here we could probably divide everything by 4 and get away with it. So let's do that. 8 divided by 4, well, that's 2. 4 divided by 4, well, that's just 1. So in this case, -1y. And then, of course, 8 divided by 4 is, or excuse me, 0 divided by 4, rather, is still just plain old. What do you know? They're identical. All right, even though they do not look alike, to start with, they are identical in every way. So this is one of those infinitely many solutions. They end up exactly the same. So we got our answer. Infinitely many solutions. And the reasoning would be simple. The two equations are identical. All right, we were able to work through that and find, yep, while they look different to start, they're actually one and the same. All right, let's try this next one. We've got 7, 3, and 1, so greatest common factor is 1 there. That looks good. 14, 6, and 0. Well, I noticed that both of these are divisible by 2, so let's do that real quick. We'll divide this bottom one by 2. The top equation doesn't look like it needs to be altered. So 7x plus 3y equals 1, so that looks good. Let's go ahead and divide out. 14 divided by 2 is 7. All right, well, this is looking like they're the same. 6 divided by 2 is 3, so 3y, so those look like they're the same. 0 divided by 2 is, of course, 0, and then we need to pause. These are not identical. They're close, very close, I'll grant you that, but they are not the same. This is a no solution scenario. Notice in this case, the left sides are identical, but we said the right sides are different. That's exactly what we've got going on here. Left sides are the same, right sides are different, so no solution. All right, if we were to rewrite those in slope-intercept form, we'd have the same slope, but different intercepts. They'd end up looking something like that, where we've got parallel lines. So yeah, no solution. Again, some of these are very obvious, some of them a little bit tricky, but we'll work through them. Let's take a look at this last one. I do notice that our numberings seem to look alike. Let's see if that pans out. -7, -1, and 3. Well, the one thing that bothers me is this -1 business. I could technically divide everything here by a -1 and try to work things out. So I'm going to do that here. This bottom one, 7, 1, and 3, no common factors there, so I'm going to leave it alone. All right, so let's work it. Bottom one here, 7x, y, and 3, they didn't change. Up here, I'm going to divide everything by a -1 and see what falls out. So -7 divided by -1 is just 7. All right, so those seem to look alike. -1 divided by a -1 is a +1. So, okay, those look alike. 3 divided by -1 is -3. Well, what do you know? The exact same scenario here. Even though they look a lot alike, we get very different outcomes at the end. So again, left sides are the same, right sides are different. Again, no solution. All right, and a reason simple. Left sides are identical, right sides are not, and that's how we know we have a no solution scenario. So again, solving by inspection can help you not necessarily get the solution. You know, for example, in a one solution scenario, we would need to work through that. And in this case, I would probably multiply this bottom equation by 6. That way we could eliminate those and solve the system that way. What is nice about inspection is that it does allow us to solve these infinitely many and no solution scenarios like that without having to do all the work. So much, much easier and quicker. However, if we do get a one solution scenario and are asked for the solution, we would have to continue work like we did in our last lesson. So keep that in mind. All right, the second thing we're going to do, besides knowing how to deal with one solution, no solution, and infinitely many by inspection, we're also going to take a look here at some word type problems. So again, we'll just solve each system. We'll write our solution as an ordered pair. And in those cases where we've got actual values like dollars or bagels or whatever, we'll talk about that. So here's our first one. It says the sum of two numbers is 82. Okay, we can do that. And their difference is 26. So the first thing that I would tell you to do with a problem like that is set up what your two numbers are. So we'll let x be our first number. And we'll let y be our second. All right, again, we call this defining the variable. We know that x and y are worth. So let's reread it. Remember, every time we solve a system, it's going to approach the problem from two different perspectives. So like in our last lesson, we looked at, say, a rental car situation, trying to figure out which two rental car agencies would be cheaper. This time, we're viewing our situation from two perspectives. The first perspective is that we're viewing it from a sum. All right, in other words, we know what they add up to. So in this case, the sum is addition, so I can take, let's write our system in here. I could take our first number, add it to our second number, and it says we should end up at 82. All right, and then it says their difference. So again, if I took my first number and subtracted my second number, that we would end up at 26. Cool, so there's my system. All right, we need to find each of the numbers. Well, one thing that I noticed about our system going right into it is that we have a positive y and a negative y. So if we're solving by elimination, I don't have to multiply anything. My system's actually set and ready to go as is. So I'm going to go ahead and actually, that's kind of hard to read. I'm going to rewrite that in pen just to make that a little bit easier to read. There we go. That's looking a lot better. That looks a lot better. So again, our top equation represents our sum. The bottom equation represents our difference. Oh, much better. And notice, positive y and negative y, if we were to add these two equations together as they are, we could go ahead and eliminate the y variable. So let's go ahead and do that. X plus x, well, that's just 2x. Positive y and negative y, we said those eliminate, so who cares? 82 and 26, that looks like 108 to me. All right, cool, looks good. To get x, we'll divide both sides by 2. So x in this case, let's see, that'd be 54. 54, cool. So if we're writing our solution as an ordered pair, our first number is 54. Now we just got to come up with the second number. All right, well, that shouldn't be too bad. Let's look back at our original equation. It says if I take x plus y, it should equal 82. We already know what the first number is, so x plus y is 82. Let me put our first number back in. 54 plus y equals 82. Cool. To get y, all we're going to have to do is take 82 and subtract by 54. So that looks like 20, what would that be, 28? 28? Yeah, 28 looks good. And then that would be our second number. So our first number, 54, second number is 28. If we add them together, we get 82. If we subtract them, we get 26. Yeah, that looks good. All right, let's try another one. This go around says, Mr. Lamar buys 8 cups of coffee and 2 bagels one day and pays a grand total of $31. Okay, cool. It says Mr. Morse buys 3 cups of coffee and 3 bagels on the same day, so we're assuming the prices for bagels and coffee are the same, and pays $17.25. How much is each cup of coffee? How much is each bagel? So again, we need 2 variables, and it looks like Mr. Lamar and Mr. Morse looks like we were buying the same thing. So I'm going to let X, I'm going to let that be coffee. So cups of coffee. There we go. And we'll let Y be the number of bagels. All right, cool. Now remember, we need 2 different points of view. Just like up here, we had one point of view from their sum and another point of view with their difference. Here, our 2 points of view are myself and Mr. Morse as we bought our different breakfast foods. So let's start with me. It says that I bought 8 cups of coffee. Well, I could take 8, multiply that by X, right? And that would tell me, again, my cost for 8 cups. There we go. And add on to that my 2 bagels. So 2 bagels at X, or excuse me, at Y price. I wrote the wrong variable there. And it says all together, so my 8 cups of coffee at one price and my 2 bagels at a separate price, all together give me $31 as a total. Okay, cool. Let's try for Mr. Morse. Mr. Morse must not have been as thirsty as I was that day, apparently, because he only buys 3 cups of coffee. But he does buy 3 bagels instead of 2. And we're told his dollar amount is $17.25. Cool. So what we need to do now is to try to solve this particular system. Now I don't have near enough space, so I'm going to do it over here. But I do notice one thing. 2 and 3, for the y's there, I could multiply this top equation by 3 to make that a 6. I could multiply this bottom equation by a -2 to make this a -6y, and then we could eliminate. So I'm going to write that down to remind myself right here. Let's see. This top number, or top equation rather, I'm going to multiply everything by 3. And then in the bottom one, I'm going to multiply everything by -2. And that's how I'll rewrite this. Okay, so let's do it. We'll write it over here just to give ourselves plenty of space to solve this out. So 8 times 3, that is 24x. Make sure I get my variables right. 3 times 2, that is 6. And then 3 times, goodness gracious, 31, that is 93. Looks good. All right, let's try the bottom. -2 times 3, well, that's -6x. -2 times 3, again, -6y. And then -2 times 17.25, good gosh, what is that, 34.50? Let me double check that. -2 times 17.25, we don't want to do something, yep, 34.50. I did do that right. Look at that, I'm so proud. -34.50. Excellent. So now that we got that together, we've got our 2 variables here. The coefficients are the same, so let's add them up and let's start eliminating. So 24 and 6x, both of those are like terms. We can combine them. That would give us, what is that, 18x. That looks good. Obviously, +6, -6, who cares? Those cancel out. And then on the other side here, I've got a +93 up top, and then I'm taking away that, what did we say it was, 34.50. Cool, so I'm getting, what is that, 58.50? Does that sound right? 58.50. And again, I'm writing the zeros here since it's a dollar amount, just to keep that together. Now, let's go ahead and divide it out. In order to get x by itself, we'll divide both sides by 18. And that gives me a, what was x again? X was cups of coffee, cups of coffee. So x is $3.25. So as an ordered pair, we could write 3 1/4, comma, and now we can get our bagel price. Now, notice since we have this, we could plug it into either of those equations and get a good answer. In this case, I'm not sure it really matters which one we work with. We're going to be dealing with decimals regardless. So I'm going to grab the second equation there, in this case Mr. Morse's equation, for no other reason than the numbers are small. That's my only reason there. So we'll use 3x plus 3y equals 17, what do we say, 17.25, 17 1/4. Cool. We'll take the x out and put our $3.25 in plus 3y equals 17.25. Looks good. All right. So $3.25 multiplied by 3 is multiplied by 3. There we go. Is 9 and 3/4. 9.75 plus 3y equals 17.25. Let's take the 9 3/4 away. So 17.25, we'll subtract our 9, and what is that, 75 cents? 75 cents, good lord. 3y equals $7.50, $7.50. We'll go ahead and divide that by our 3. So each, what was y again? Y was bagel. Each bagel cost looks like $2.50. So our other number here is $2.50. So how much is each cup of coffee in each bagel? So there's our ordered pair. So if we graphed it, notice that'd be very tough to read on a grid, especially if we drew it by hand. I'm not sure I don't want to try and make that out by graphing. But how much is each cup of coffee? So we can say each cup of coffee is $3.25, kind of expensive for a cup of coffee. And each bagel is, what do we say, $2.50. Cool. So again, that's how we would work that problem out by elimination. And again, based on our answer, if we were to try to graph that, that would be a royal pain. This first one, if we were to graph it, again, our grid would have to be so large to get numbers that high. This one, it would occur at a non-intersection point, and with those decimals there, that would be terrible, absolutely terrible to try and graph out and figure out what we've got. All right, but let's look at our last question. We got to make fun of Moss at some point in this video, right? So let's take a look. Farmer Moss. Why not, right? Farmer Moss looks out his window one day and counts a total of 64 legs on a total of 20 animals on the farm, all right? If he only has sheep and chickens, how many of each does he have? And since he's from Owensboro, it's fitting that we're talking about sheep. Hint, in case you didn't know. Sheep have 4 legs each and chickens have 2 legs each. Again, put that on there just in case you didn't know that. So let's look at our situation. Remember, we need 2 variables. So it looks like we were told up front we're going to be dealing with sheep and chickens. So I'm going to let x be our number of sheep. And we'll let y be our number of chickens. Here we go. And we need 2 points of view, because notice here we had my situation, Mr. Morse's situation, or here, sums and differences. 2 different points of view for the same problem. Our situation here is that we have a total number of, we'll write it over here. We've got a total number of animals and a total number of legs. So our 2 different equations need to reflect that. Let's start with animals first, because that's going to be easier. So if I have so many sheep, x number of sheep, and so many chickens, so y number of chickens, I'm going to get 20 animals total. So there's our first equation. All right. Let's look at our second one. We know that sheep have 4 legs each, so I could write that as 4x, 4 legs times each number of sheep to get that total number of legs. And then we've got 2 legs for each chicken. So I could take the number of chickens times 2 and get the number of chicken legs we've got. Grand total number of legs we said was 64. Excellent. So let's look. How could we solve this particular system? Put our bracket in there. There we go. So how could we solve this? Well, there's a couple of ways. I think the easiest in this case would be to go ahead and let's multiply this top equation by -2. If we do that, we can get our y's to go away, and that would work well. Another way to do it is we could divide everything here, say by -2 at the bottom. That way our y's could disappear that way as well. I don't want to work with negatives in quite that way. This top method will work fine. Don't really want to divide by negatives there on the bottom. That's probably not going to end well. So let's see what we get. We'll rewrite our situation here, so we'll do it underneath. Negative 2 times x is negative 2x. Negative 2 times y is negative 2y. Negative 2 multiplied by 20 there is negative 40. And there we go. Bottom equation never changed. So 4x, 2y, and 64. There we go. All right, well, let's start adding. Notice I've already got those set for elimination. We can just add our two equations together, and we're off to the races. Negative 2 add 4 is 2x. Looks good. Negative 2 and positive 2. Who cares? Negative 40 and 64 give me, what is that, 24. Looks good. We can go ahead and divide and get our number of x's, in this case the number of sheep. So we divide by 2, x equals 12. Cool, so we're asked to write it as an ordered pair first. Let's do that. We have 12, looks like 12 sheep on the farm. All right, cool. Let's take that number and plug it in. I think that top equation is going to be a lot easier to work with just because it's x plus y equals 20. So 12 plus, that was our x, plus y equals 20. Looks good. We'll subtract 12 on both sides. That gives me y on one side, and if I subtract 12 there, that is 8. Looks good. All right, well, let's double check though. If I take 12 plus 8, do we get 20? Yes, that seems to work. So this solution seems to fit in that first equation. Let's try this one. All right, let's double check ourselves. We'll use calculator here just so you can see how I'm doing it. We'll do 4 times 12. Remember, 4 legs for each sheep. And we'll add on to that 2. Remember, 2 legs for each chicken. And we need to get 64 legs total. Yep, looks good. Our solution seems to work. So we can say that there are, let's see, there are 12 sheep and 8 chickens on the farm. There we go. We'll make it exciting. So that's what we're doing today, guys and gals. We're still using elimination, so we'll use it to solve maybe some word problems, maybe just some standard nondescript systems as well. We'll also be using, not elimination, we will be doing elimination, but we'll be using inspection to also figure out what kind of solution we have. So that way, once we get our systems, notice in each of these, both the left and right-hand sides were different, so we knew we were going to come up with one solution. But we'll still use inspection on those more generic cases to figure out, do we have one solution, maybe no solution, or infinitely many. Again, please write down your questions if you've got any. That way we can talk about them in class. Guys and gals, I want to answer your questions as best I can. Have a good day, and I look forward to seeing you.